In this video, I'm going to explain the difference between an indefinite integral and a definite integral. An indefinite integral is an integral that looks like this. Okay, there's no number at the bottom of the integral sign. There's no a and b at the bottom and top of the integral sign. So what an indefinite integral really is an antiderivative. So when you see this symbol, this means find the antiderivative or find the general form of the antiderivative of f of x. So as a quick example, if we see the integral of 2x dx, what that's asking us for is to find the antiderivative of 2x. So find a function whose derivative is 2x. And of course, x squared could be an answer. Okay, the derivative of x squared is 2x. But x squared plus 5 also works. Okay, so it's not the only antiderivative that works. In fact, x squared plus any constant c will be an antiderivative. So that's the general form of the antiderivative of 2x. And that's what an indefinite integral is asking for. Now, a definite integral is an integral where we have the a here and the b here. We're integrating from one number to another number. And what this means is to find the area, okay, or the net signed area between the graph of f and the interval AB along the x-axis. Okay, so what do we mean by net signed area? Well, I'll explain that in just a second. But one thing I do want to point out is that a definite integral really has kind of a technical definition that involves Riemann sums, but we're not going to worry about the technical definition right now. We're just going to kind of get the basic idea of what a definite integral is all about. Okay, so find the net signed area between the graph of f and the interval a to b. So what do we mean by net signed area? Okay, if we have a function that is a positive function, meaning that it lies above the x-axis all the time, then the integral from a to b of f of x dx, okay, the definite integral, means to find this area. So net signed area in that case just means area. Okay, so the integral from a to b of f of x dx, okay, what that means is find this area. Okay, so the net signed area in that case is just the area. Okay, but suppose we have a function that is sometimes positive and sometimes negative. So here's an example of a function that is sometimes above the x-axis and sometimes below the x-axis. Okay, so let's go from a to b here. Okay, we really have three regions here that are between the graph of f and the interval a to b along the x-axis. And so if we're asked to find the integral from a to b of f of x dx, okay, that definite integral, what does that mean? Well, I didn't give you a formula for this function, but let's suppose that we know that the area of this region here is 7 units. Let's suppose that we know that the area of this region is 2 units, and that the area of this region is 3 units, or square units, I should say. Okay, now what is the integral from a to b of f of x dx? Well, it's the net signed area between the graph of f and the interval a to b. So what do we mean by signed area and what do we mean by net signed area? Well, this area in the middle here, since it's below the x-axis, counts as a negative. So the integral ends up being 7 plus negative 2 plus 3, which turns out to be 8. Okay, so the definite integral from a to b of this function f of x dx turns out to be 7 plus negative 2, because this region is below the x-axis. It counts as negative. That's why we call it signed. And then we're adding them all up and sort of netting them. We take 7 plus negative 2 plus 3 gives us 8. That is the definite integral. Now notice that's not the same thing as the total area. Okay, so this is the net signed area. Okay, the total area of the shaded region would be 7 plus 2 plus 3, which is 12. Okay, but the total area is not what the definite integral is asking you to find. The definite integral is asking you to find the net signed area. So that's what we mean by net signed area. Okay, now here's a question that naturally arises is why is the notation so similar for such seemingly different concepts? And the different concepts I mean are definite integrals and indefinite integrals. Okay, so there's an indefinite integral. Here is a definite integral. Notice that they mean two totally different things. These definite integrals have nothing to do, the definition has nothing to do with antiderivatives. Okay, and the definition of indefinite integrals has nothing to do with area. Okay, so why do we use such similar notation for totally different concepts? We have the same integral symbol on both sides here. We have the same dx right here. And in fact, we use the same terminology. We call them both integrals. Okay, but they mean totally different things. Indefinite, again, means find the antiderivative of f. And definite integral means find the net signed area between the graph of f and the interval a to b. So the connection, it turns out, is the fundamental theorem of calculus. The fundamental theorem of calculus says that the way to actually calculate a definite integral, the way to actually find that net signed area is by doing an antiderivative, okay, doing an indefinite integral. Okay, so let's look at a couple examples. Let's begin with the definite integral from 0 to 5 of 2x dx. And let's calculate this integral in two different ways. Part A, we'll do it without using the fundamental theorem of calculus. Okay, we'll use geometry to actually do this. And part B, we'll do this using the fundamental theorem of calculus. Okay, so first of all, let's graph our function, 2x. I can do this. Okay, here there's f of x equals 2x. And let's look at the interval from 0 to 5. Now this point up here is the point 5 comma 10, because when we plug in 5 for x, we get 10 as a result. And what we're really trying to find, if we're doing the definite integral from 0 to 5, is the net signed area between the graph of this function and this interval here from 0 to 5. Now, since the function is positive on that interval 0 to 5, what we're really looking for is not just the net signed area, we're looking for the area. Okay, that's what the net signed area actually is. Okay, so it turns out, though, that the area of this region is not hard to calculate. Right, because this region is just a triangle, and we know that the area of a triangle is 1/2 the base times the height. Now the base of this triangle is 5, and the height of this triangle is 10, so 1/2 of 5 times 10, or 1/2 of 50, ends up being 25. So what we can say is that the integral from 0 to 5 of 2x dx turns out to be 25. Okay, now if you've done integrals before, definite integrals before, you might think, well, that's not the way I normally calculate integrals. I do these type of integrals by doing antiderivatives. Okay, well, that's really what the fundamental theorem of calculus is all about. Okay, so part B, we're going to use the fundamental theorem of calculus to calculate that definite integral. So the integral from 0 to 5 of 2x dx. Okay, according to the fundamental theorem of calculus, the way to calculate this area, this net signed area, is one way to do it is by doing an antiderivative of this function. So an antiderivative of 2x would be x squared. Now I could put x squared plus 5, x squared plus 1, x squared minus 8, or x squared plus any value of c, but all we really need is one antiderivative. And x squared is a perfectly good antiderivative of 2x. And we're going to evaluate this from 0 to 5. So what that means is we'll plug in the 5 first, the top number first, and we'll plug in the 0 and subtract. So what we get is 25 minus 0, or 25. Okay, and notice that our answers are the same. Okay, so the fundamental theorem of calculus really did give us the correct answer, gave us the same answer that we found when we used geometry. Okay, now that function that we looked at was always positive, so we didn't really get the idea of net signed area in that. We just had the idea of area. So let's do a different example, and this one will sometimes be below the x-axis. So let's take a look at the integral from 1 to 9 of 2x minus 6 dx. And we're going to calculate it two ways. One, using the fundamental theorem of calculus without using it, and the second way will be using it. Okay, so 2x minus 6. Okay, this would be minus 6 down here. And where it crosses the x-axis is 3. Okay, 1 is over here somewhere, and 9 is way over here somewhere. Not drawing this to scale very well. But what we'll really end up with is two regions here. So this function is f of x equals 2x minus 6. This point up here is 9, comma, well, if we plug in 9, we would get 18. 18 minus 6 is 12. Okay, 9 comma 12. This point down here, okay, if we're over here at 1, this would be 1 comma what? Well, if we plug in 1 into the function, notice that we get minus 4. Okay, 1 comma minus 4. Okay, so what we're trying to find is the net signed area. Okay, so let's look at the area of this region. Okay, the area of this region. Again, it's a triangle, so we're just going to look at 1/2 the base times the height. The base is 6. You see here, between 3 and 9, that's the base. And the height is 12. Okay, 1/2 of 6 times 12, that would be 36. Okay, so 36 is the area of this region, but we also have this region here that's below the x-axis. Okay, between 1 and 3, it's below the x-axis. So let's look at, sorry, it's a little cluttered here. Let's look at the area of this region. Okay, 1/2 the base times the height. Now the base has a length of 2 and the height has a length of 4. Okay, so 1/2 of 2 times 4, so that would be 4. Okay, so the area of this region below the x-axis is 4 square units. The area of this region above the x-axis is 36 square units. So what is the net signed area, right? So if we calculate the area from 1 to 9 of 2x minus 6 dx, it turns out that it'll be 36 plus a negative 4. Okay, or a negative 4 plus 36, which ends up being 32. Okay, so the integral from 1 to 9 of this function is 32. Now let's compute this using the fundamental theorem of calculus and see if we come up with the same result. Okay, what we have is the integral from 1 to 9 of 2x minus 6 dx. And the antiderivative of 2x is x squared. Antiderivative of 6 is 6x. Again, we don't have to put the plus c there since we're doing a definite integral. And let's plug in the 9 everywhere we see an x, and then subtract what we get when we plug in 1 everywhere we see an x. So what we have is 81 minus 54 minus 1 minus 6. 81 minus 54 is 27, and 1 minus 6 is minus 5. So what we end up with is 27 plus 5, which is 32. Okay, now notice that's the same answer that we had up here. Okay, our two answers are equal. Okay, so we see again that using the fundamental theorem of calculus, it allowed us to find that net signed area. Okay, we got the same result that we did when we used geometry. Okay, now both of the previous examples that we've done, we were able to use geometry for. Okay, and the reason was because our regions were nice regions. They were triangles. Okay, and if our regions are nice regions like triangles or rectangles or circles, we have formulas from geometry to help us calculate the areas of those type of regions. But let's do an example where we have to use the fundamental theorem of calculus. We can't use geometry. So let's look at the integral from 0 to 6, so definite integral from 0 to 6 of x squared dx. Okay. Let's say this is 6 here. This will be 6 comma 36 up here. I guess it's not really to scale. The point probably should be a lot higher than the way I've drawn it. Okay, and our function is f of x equals x squared. So what we're really looking for is what is the area of this region between 0 and 6 that's underneath our function x squared. Okay, and since the region is always above the x-axis, when we say net signed area, we really, in this case, just mean area. Okay, what's the area of that region? Now notice, again, the region is not a perfect triangle. This side here is bent right there. And it's not a rectangle or a circle where we have a nice formula for geometry. So we have to use the fundamental theorem of calculus. So if we calculate the integral from 0 to 6 of x squared dx, we get x cubed over 3, right? Or 1/3 x cubed. If you take the derivative of that, you'll get x squared. And we're going to plug in 6, and we'll plug in 0. And what we end up with is 216 over 3 minus 0. And 216 over 3 is 72. Okay, so 72 square units, that's how much area this region is right in here. Okay, now actually, does that make, it's always good to kind of check to see, does that sort of seem like a reasonable answer? What if we had just taken the triangle right here and tried to find the area of this triangle? Well, I would expect it to be bigger than the area of this region right here. In fact, what is the area of that triangle? Well, the area of that triangle would be 1/2 the base, which is 6, times the height, which is 36. Okay, and 1/2 of 6 times 36 is 108. Okay, so the area of that triangle is 108. Yeah, I guess it makes sense the area of this region should be less than that. Yeah, 72, that certainly seems reasonable. Okay, so again, this is just some scratch work over here. Okay, now I want to illustrate one of the reasons why we use net signed area instead of area when we're doing definite integrals. Okay, what good is net signed area as opposed to just area? Okay, and also why might it be useful to know how to find the area underneath a curve? So let's look at a quick example. Suppose you drive on a straight road at 70 miles per hour for 3 hours. How far did you travel? Okay, well, of course, it's easy to get the answer. Just do 70 times 3, and you'll get 210, and that's 210 miles. Okay, that's an easy calculation, but let's look at this graphically. Okay, let's make a time axis here, and let's make a velocity axis here, v. Okay, and let's suppose that you're going 70 miles per hour. So let's graph the velocity over the course of 3 hours. Okay, your velocity is constant. Your velocity is constantly 70. And notice what happens if you integrate this function. Well, you would get the area underneath that curve there. But what is this area? Okay, well, the area of that region, it's 3 by 70. Okay, or 70 by 3, it's 210. So notice that the area of the region underneath the velocity curve was really just a straight line because you're going constantly 70 miles an hour, gave you how far you traveled. Okay, let's change the example a little bit. Now let's suppose you drive 70 miles per hour for 3 hours and then you drive 50 miles per hour for 2 hours. How far did you travel? Okay, well, let's do this using our graph again. Okay, so we're going to have a 70 miles per hour for the first 3 hours. Okay, and then for the next 2 hours, so I guess from time 3 to time 5. So again, this is t, this is the velocity here. You'll drive 50 miles per hour, so this would be 50 right here. Okay, the area underneath this curve should give us how far you traveled. Now, I noticed that it really is impossible to go immediately from 70 miles an hour to 50 miles an hour. You'd have to slow down. So what's happening right here at this time is really impossible to actually do it. But just to simplify the problem, let's suppose that you're going 70 miles an hour for 3 hours, and then just immediately you jump to doing 50 miles an hour for 2 hours. How far did you travel? Well, notice the area underneath this part here, okay, is 210, right? It's 70 times 3, which is 210. And the area underneath this part, well, how far did you travel during these 2 hours? Well, you traveled 50 miles an hour for 2 hours. Okay, notice that the area here, this is 2 by 50. Okay, or 50 times 2 gives you 100. Okay, so you traveled 210 miles in those first 3 hours, and you traveled 100 miles in those next 2 hours, so you traveled a total of 310 miles. Okay, and notice that's the area underneath the curve. Now this example is a little bit unrealistic for several reasons. One is because you can't jump immediately from 70 to 50. And it's also unrealistic to assume you're going to be going exactly 70 miles an hour. Most times you'll be going a little faster than 70, a little slower than 70. You're speeding up, slowing down. And in that case, you get a nice curve here. And if we have a nice curve, well, how do we find the area underneath a curve? We wouldn't get these nice rectangular regions. Well, that's what you need the fundamental theorem of calculus for. If you had a nice formula for your curve, you could find the area by using the fundamental theorem of calculus. Okay, but what I really want you to see here, and this is the important example here, is this. Let's suppose you drive 50 miles per hour for 4 hours, and then you drive in reverse. Okay, I don't know why you do this, but drive in reverse at 30 miles per hour for 2 hours. Okay, and then you drive forward again at 20 miles per hour for 2 hours. So how far did you travel? Okay, now it depends what you mean. Notice that you traveled 50 miles an hour for 4 hours. You traveled forward that far, so you went forward 200 miles. Okay, and then you traveled in reverse at 30 miles per hour for 2 hours, so you went in reverse 60 miles. And then you went forward again at 20 miles per hour for 2 hours, so you went forward 40 miles. So how far did you travel? Well, the question is a little bit ambiguous. Okay, one way of saying how far you traveled is what's the total distance that you traveled? Well, you traveled 200 miles plus 60 miles plus 40 miles. You went 300 miles. Okay, that's the total distance you traveled. But another question that you could ask, and this sounds real reasonable to ask this question, is what's the distance from where you started to where you finished? Okay, if you went forward 200 miles, then backwards 60 miles, okay, and then forward 40 miles again, then you're really 180 miles away from where you started. That's what's called the displacement. Okay, and if you calculate a definite integral, you're really finding the displacement. Okay, if we were to graph this function, okay, here's t and here's v. So I think we said we were going forward at 50 miles an hour for 4 hours. Okay, and then for the next 2 hours, we're going in reverse at 30 miles an hour for those 2 hours. And then we're going forward again for 2 hours at 20 miles per hour. Okay, and if you notice, we have 3 regions here, okay, between the curve and the x-axis, or it's really the t-axis right here. That's a 6, by the way. And if we called this function here, if we called this function v of t, okay, the function that's right up here, and it's also down here, and it's also up here. If we called this function v of t, what is the integral from 0 to, I guess it would be 8, okay, this number 8 here, of this function v of t, your velocity? Okay, notice, this would be dt here, notice that what you would have, first of all, is this area would be positive. That would be 200 miles, would count as positive. This 60 here, this area is 60, okay, it's 2 by 30. It would count as negative. And last of all, we'd have a plus 40 right here. And what does that give us? It gives us 180. So what the integral actually calculates is the displacement. Okay, the integral of the velocity function from some a to b, in this case it's from 0 to 8, the integral gives you the net signed area between the graph of v and the t-axis, but the net signed area gives you the displacement. Okay, it doesn't give you the total distance traveled, it gives you the distance from where you started to where you finished.